Hey everybody. This week we're going to be doing a video talking about the basics of communicating with space hardware as far away as Mars or further in the solar system even. Start by talking about radio waves just in general. As you probably know, having taken physics earlier on, there's the amplitude, how tall the wave is, how much power it has. There's the frequency, which is how often you can go from a peak back up down to a peak over time. And there's the wavelength, which is how long distance is between a peak and a peak or a trough and a trough. And all these waves, the velocity and the frequency equation on top is just the speed of light. Everything here moves at the speed of light. And you think moving at the speed of light, you'd be able to communicate with anything very, very quickly. And that is the case for almost anything on Earth, or even communicating with the ISS. The International Space Station has less than 1/10 of a second of delay, which is why you can have video conversations with astronauts up there seemingly normally. However, when you're getting as far as the moon or even Mars, that time delay, even moving at the speed of light, can become substantial. And it's the kind of thing where, in the case of this project we're doing this semester, communicating from Earth to Mars in real time is not going to be possible. Depending on when in the orbit of both Mars and the Earth around the sun is, the communication delay from Earth to Mars can be anywhere from 5 to over 20 minutes. And you can see on this graph here that it scales linearly as the further away you get. Now, talking to stuff on the surface of Mars or around Mars nowadays, there was in the early 2000s a Mars reconnaissance orbiter shown on the bottom left of this slide that allows for communication with the rovers. The rovers don't have antennas or power systems capable of reaching Earth in the X-band frequency wave. But with the Mars reconnaissance orbiter, which was sent over there to not only take pictures and do science of its own, but act as a relay station for the lower powered radios on the Mars orbiters to get back to Earth. And that's where it stands right now. In the 2040s, when this project takes place, who knows what the infrastructure is going to look like. And the Earth side of things, we can't have giant antennas in spacecraft. That would be cost prohibitive, power prohibitive, what have you. So we make up for that by having giant antennas on Earth, and this is called the Deep Space Network. Deep Space Network is composed of 3 120-degree apart ground stations. One can pick up from the other. One in Spain, one in Australia, and one in Southern California. These massive antennas can both send out commands and also receive commands. And if you look at this diagram of one of those antennas on the right, you can see that the giant, larger parabolic antenna receives the signal once it's been dialed in. That gets reflected up to a smaller mirror in the top, which then gets bounced through a series of mirrors down into the bottom, where the ones and zeros, the peaks and the troughs of the radio wave sent from the Mars Reconnaissance Orbiter or a lunar spacecraft or one of the Voyager probes or New Horizons or any of the many space missions launched further than low Earth orbit, that gets decoded and sent to the computers on the ground. And the nice thing about having the 320-degree apart antennas is that as the Earth is orbiting, or the Earth is rotating around its axis, communications can remain uninterrupted and allow for nonstop communication with Mars rovers, orbiters, anything going out that far. So as we continue through the semester, I'll be doing maybe a few other videos talking about the specifics, and as some of you mentioned in your PDRs, the possibility of optical communications as a better method for communicating that far out going forward. Thanks.